All right, in our last video in section 15.3, we talked about how we can estimate the area underneath the curve by using rectangles. We call this a Riemann sum. We started off by using two rectangles, but remember that was just an estimate. Some of the estimates were overestimates when the rectangles were above my curve. One of my estimates was an underestimate because they were below my curve. But how could we get a better estimate? Well, we tried using midpoints, which got us a better estimate, or we can use more rectangles. We can use 4 rectangles, we can use 8 rectangles, we can use 16 rectangles. The more rectangles we use, the better and better our approximation is going to be. So if you look at these pictures, you notice that I can use more rectangles, that has 10 of them, and it covers more of the area underneath my curve. But if I use 20 rectangles, I cover even more area underneath my curve. There's less white space that I haven't covered. And the more rectangles you use, the better your approximation is going to be, right? We can figure out what the widths and the heights are, base times height of each of these rectangles, by first figuring out what unit I'm going to cover, what interval I'm going to cover. Do you remember in our example we started at 0 and we went all the way to 2? We knew that was 2 units wide. And when we divided it by 2 rectangles, that told us that each of our rectangle widths was going to be 1. Or when we divided it into 4 rectangles, we knew that each width of our rectangle was going to be 1/2. Well, we can figure out the widths, or we call them delta x's, of any rectangle if we know our interval length, so b minus a, and then we divide it by however many rectangles we have. So if I know that I'm going to go from, let's say, 1 to 9, if I'm going to start at 1 and I want to go all the way to 9, and I want to find the area underneath the curve from 1 to 9, well, the units between 1 and 9, 1 taken away from 9, is 8 units total. If I want to divide that into 4 different rectangles, I can take that 8, divide it by 4, and I know that each of my little widths of my rectangles is going to be 2 wide. So all my little bases are going to be 2. So another symbol for that, again, is what we call delta x, the little widths of all of our rectangles. And we know that we can find the area of any rectangle by doing our base times our height. So this is just base times height. Remember, we found the heights of our rectangles by figuring out the y value that corresponds to the height depending on where we are on the x. We can find the area of all the rectangles by adding up all of our different bases times heights. So you can see this little sigma notation is just a representation of how we're going to add up a whole bunch of different terms, all of our little areas of our rectangles, starting at 1 and going up to a certain number of rectangles. If we wanted 4, if we wanted 8, if we wanted 16. But how are we going to make this an exact estimate? Well, we can take our bases times our heights, we can add them all up, but how many rectangles would I need in order to get an exact estimate? Well, we would need this number to eventually go to infinity. We can't possibly, though, sit there and do base times height plus base times height plus base times height an infinite number of times. So what we're going to learn now is that really taking these areas of all these little rectangles, an infinite amount, is the same thing as doing what we call definite integral. We've seen an indefinite integral where we don't have the numbers on top and bottom. We can find the antiderivative, right? But what this is we're really finding the area underneath the curve from A to B. So if we were doing the area underneath the curve of a function and we wanted to start at 1 and end at 9, we could just find the antiderivative and figure out what its value is from 1 to 9. So another interpretation of integration is finding the antiderivative. Another interpretation is finding the area underneath the curve from A to B. So back in our first example, when we divided up into 2 rectangles and 4 rectangles, and we used left endpoints and right endpoints, and we were using those to estimate the area. Do you remember the square root of 4 minus x squared was our equation that we were trying to find the area underneath? And we were going from 0 to 2. Well, now, instead of approximating, we could actually just integrate that function from 0 to 2 and find an exact area underneath the curve. We end up getting an exact area of pi, approximately 3.14. Do you remember when we did it by hand, we got an overestimate, what was it? We got an overestimate of 3.7, but our rectangles were too high. We got an underestimate of 1.7. Well, the actual exact area is 3.14 blah, 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 whatever pi is, right? And so now we can find an exact area underneath the curve because it's the same as integrating from A to B. All right, before we go into some integration techniques, let's still approximate. Let's practice one more time. Example number 2 is going to ask us to approximate the integral of x cubed from 0 to 4. So what that's really saying is that you have the graph f of x is equal to x cubed, and we want to find the area underneath that graph from 0 to 4. So if you were to draw a picture, like my picture down here, we know that an x cubed graph kind of snakes its way through kind of like this, and we know we want to find the area underneath the curve from 0 to 4, so my area is this little piece right here. It's not an exact triangle, and so I can't really use geometry to find the exact area. So what we would have to do is estimate the area using our rectangles. In this problem, it's asking us to use 4 rectangles of equal width, whose heights are the values of the function at the right endpoint and then again at the left endpoint. So we're going to do 2 different estimations. Let's first start off with doing the right endpoint. Remember, it told us that we wanted 4 rectangles. So let's figure out if we want to do base times height plus base times height plus base times height plus base times height, 4 rectangles, what the bases of each of these rectangles are going to be. If you notice on my graph, it told us that we want to go from 0 to 4. So 0 to 4 is a total of 4 units, right? That's my b minus a. And they told us in our problem that we wanted to divide it into 4 rectangles. That means n is 4. We have 4 rectangles. If I take my whole entire interval from 0 to 4, that's 4 units, and I divide it into 4 rectangles, how wide is each of our rectangles going to be? 1, right? So that means our widths, or our delta x's, are all 1. The width of the first rectangle is 1, the width of the second rectangle is 1, the width of the third rectangle is 1, and the width of my fourth rectangle is 1. If all the bases are the same, can I GCF out that 1? All right, so now all we have to do is find the heights of all of these rectangles. And we want to use right endpoints for the first one. So I'm imagining being on my first rectangle. If I'm at the first rectangle and I want to use the right endpoint, I want to follow the right side of the rectangle up to my function and over. Now I'm imagining I'm on the second rectangle and I want to follow the right endpoint up till I hit the function and follow it over. Why don't you pause the video and draw me your 2 last rectangles using right endpoints. Following it up from the right, following my last one up from the right, your rectangle should look like this. So if we're using these 4 rectangles, is our estimate going to be an overestimate or an underestimate for the area underneath my curve? Because my rectangles are over, then it's going to be an overestimate. My answer is going to be too big, but that's okay. We're just using it to estimate. Now we've got to figure out what the heights of all of these rectangles are. If I'm looking at my first rectangle, I know that the height represented this height right here, the y value when x was 1. My second rectangle had this height. This was a height when x was 2. My third rectangle had a height here. This is a y value when x is 3. And my last one had a y value, a height, when x is 4. So I'm going to use those x values to find the heights of all my rectangles so I can do my base times height. I'm going to figure out what f of 1 is, what f of 2 is, what f of 3 is, and what f of 4 is. Those are the y values, or the heights, of all 4 of my rectangles. I'm going to figure out what f of 1 is by plugging in 1 to my function. Remember, my function, my graph, was the x cubed. So 1 cubed is 1. 2 cubed is 8. 3 cubed is 27, and 4 cubed is 64. I can add all of those up and multiply it by 1, and I end up getting an approximate area of 100 square units. But remember, that was an overestimate because my rectangles were above my curve. What happens then if I use left endpoints? Let's see if I can erase this without erasing my whole graph. Ooh, pretty good. Okay, so we're back to our original graph, still an x cubed graph, but instead of using right endpoints, let's go ahead and use left endpoints. We're still covering the same interval from 0 to 4, so that's 4 total. We still want 4 rectangles, so if I take the 4 units and divide it into 4 rectangles, I know each one is going to be 1 wide, so my base are still 1. Now I just have to find the heights of my rectangles, but this time using left endpoints. So I'm going to imagine I'm standing at the left side of this first rectangle. If I go up and I go over, there's really not much of a rectangle there. It's kind of squished, right? But on my second rectangle, if I go up from the left and over, it would look something like that. My third rectangle, if I followed it up from the left and went over, it would look like that. And my fourth rectangle, if I followed it up from the left and over, it would look like that. You might notice that on all of these rectangles, they're underneath your curve now. So when we use these 4 rectangles to find the area, it's going to be an underestimate. Our answer is going to be too small. So then we can kind of compare the difference between the two. So let's go ahead and find the heights of each of these rectangles. My first rectangle, the height corresponded with an x value of 0. My second one corresponded to this height when x was 1. My third one represented the height here when x was 2, and then here when x was 3. So I'm going to find the 4 heights by doing f of 0 this time, plus f of 1, plus f of 2, plus f of 3. 4 rectangles using left endpoints. I'm going to find the y values by plugging in 0 into my function. Remember, your function was an x cubed graph. So 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. I can add all of those together and multiply it by my base, which was 1, and I end up getting 36 units squared. Remember, that was an underestimate because my rectangles were below. The 100 was an overestimate. My rectangles were too high. I know that it's somewhere in between them. Something like, I don't know, maybe 50, 60-ish, something like that, right? So somewhere in between 100 and 36. But still, those were just estimates. In order to get the exact area underneath that curve, where was it? All this little pink stuff, right? What I would actually have to do is I would actually have to integrate x cubed. Remember, integration is just an antiderivative. What is the antiderivative of x cubed? X to the 4th over 4, right? But then we would need to evaluate it from 0 to 4. We'll talk about how to do that in the next video or in the next few sections so that we can actually figure out exactly what the area is underneath that curve from 0 to 4.